Hello. After doing the teardown and repair on this Racal counter, I had quite a few people asking me why I either didn't do a modification for it or why I even needed to worry about trimming the internal oscillator. And I had to think about that because I was just gonna kind of put all the frequency stuff away for a while, but So why would I want to trim this even though I've got a Rubidium standard to plug into it? And that's a really good question, and the answer is pretty simple. It's actually nice to have the equipment stand alone. There's all sorts of reasons why that, you might need to take that counter somewhere, you might need to do something with it, and it's nice to know that, by and large, within its capabilities, it's going to be good and precise and dependable. So, having an oscillator like this is the oscillator board. I've lifted it out again. One of the problems I find with it, you try and trim it, even with a plastic trimmer, which I still haven't got, by the way. If anyone ever wants to send me one, I am joking, I will get some one day. But even with a plastic trimmer, it's really, really precise, and you can't get it spot on. It drifts around, and these are just not very good. So now, would it be worth designing a PCB for? I'm not sure. I'm certainly not going to. But what I thought I'd do today was a really quick build. And actually fit this OCXO, which I bought off eBay. It's not particularly expensive. I think it was about $15. So the total parts cost of this is probably going to be less than $25 US. I'm going to build it prototype style, and I thought, as well as doing the modification, I'll talk you through the process of how I would build a prototype, something that is a one-off, but at least it's still reasonably good build quality. Now, because I'm not going to make a PCB, I'm going to use some perf board like this, and we'll go through that. Or I'll go through how I normally construct these kind of things. So before we do that, I'm just going to talk you through the outline schematic of what I'm going to build to put in here, because there's some unique characteristics of this counter. Well, not unique, but there's specific characteristics that we have to be taken into consideration. So let me just reposition the camera, get the diagram, and let's talk through that. Okay, so this is the diagram of what I'm going to build today, or what we're going to build. It should be really simple to construct. There's really only two major components. One is the OCXO itself, which is this here. You can see, I'm not quite sure what they do to these things when they take them out of equipment. So for all of those people that were telling me that OCXOs off of eBay are cheap for a reason, while I kind of understand they're removed from old equipment, and clearly not particularly well in some cases. I'm not quite sure how that would get like that. Fact is, these do work, and they're an awful lot better than these oscillators here. So whether or not they're cheap and from eBay and they've already aged, there are actually some advantage to the ones that come off eBay. Ones like these ones, for example, is that they they've aged already. And these things do change their characteristics over time with age because of the temperature that they run at. So, and as a general rule, an OCXO that ages, the older it is, and so as long as it's reliable and as long as it's working, its characteristics tighten up, and it just gets better and better with age. So, kind of like a good wine. It's worth bearing in mind, or at least that's what I think. I'm sure other people have other opinions. Feel free to post them if you want, and let the other viewers can take a view as to whether your views are valid or not. But anyway, so I'm going to use this one today. Now, why am I going to use this oscillator? Well, before we go into the schematic, one of the problems with that Racal counter here is, unlike most counters, the OCXO connector on here doesn't have 12 volts on it, only has 5 volts. And actually, looking at the 12 volt supply inside this counter, it's certainly not up to the job of powering an oven. So one of the characteristics of this counter is I'm limited to 5 volts for the supply for the OCXO, and obviously it needs a reasonable bit of current. So looking at this one is actually a 5 volt OCXO. You can look up the part number. It's an OCXO 131-100. And it runs at 5 volts. It draws about 600 milliamps from cold. Takes about 10 minutes to get up to working temperature, or for the, well, I'll say working temperature. It takes about 10 minutes for the oven to stabilise at about 180 odd milliamps. at 5 volts, and that's pretty much where it sits then. So that's the kind of characteristic. So that's important, and I've chosen that particular OCXO and bought that on eBay from a seller, I think in China or perhaps Hong Kong, just specifically for this counter. So now, so let's have a look at the circuit diagram then. So what have we got? Well, these OCXOs are actually really simple. They've got normally a ground, obviously, 10 megahertz out, which is what we want. In this case, 5 volts in. And then this pin called VFC, or variable frequency control, or trim, or whatever. And what this takes is a DC voltage between 0 and 5 volts in this case, to tune it plus or minus, I think the specs on this say plus or minus 0.9 parts per million. Parts per billion, I think, actually. I'll have to look. I'll put the data sheet up on the blog article that comes with it that this video supports. So it's pretty easy. Basically what we've got to do is power it with 5 volts, connect it to ground, use the 10 megahertz output and trim the input frequency, trim the frequency using the variable voltage on its input to get the desired, the precise frequency. And obviously you do that after warming up. Now, there's some problems with doing that because just putting a pot between plus 5 volts and ground is really not good enough. So let's talk about why that is. Well, the plus 5 volt supply, for example, will be coming out of a classic 7805 or something like that. And those things have a temperature characteristic, which means as the temperature changes around them, so if you operate those in a cold environment, you'll find the voltage output is ever so slightly different than when they're operated in a warm environment, for example. So they're not very stable. So we need to stabilize that and get that better, not from a precision point of view, but from a temperature stability point of view, and we'll come on to that in a second. So that's one of the characteristics we have to deal with in terms of using a variable voltage control on this thing. So looking at the schematic then, these are the 4 connections. If you recall, I had to replace that connector. There's actually 5 connections, but only 4 are used, and it's keyed. So the first pin, or pin 1, is plus 5 volts. I think it's about 5.3 volts is what it measures, but it's plus 5 volts. And what I'm doing here, I'm simply a simple low-pass input filter just to take out any high frequency noise that might be coming out of here. That's almost certainly not needed for correct operation, but it certainly doesn't harm to have that. And as I've got the components here, it's no big deal to fit it either. So we'll do that. Then pin 3 and pin 5 are ground, so that's nice and easy. And pin 4 is the 10 megahertz reference or oscillator signal for the 10 megahertz input back to the frequency counter from the oscillator. So there's really nothing to do there other than just connect it up. So then we come over to here. So looking at the variable frequency control, again, nothing complex. I'm going to use a 10-turn trimmer potentiometer, or trim pot, something like that. Reasonably okay. I think this is probably 100 parts per million per degree C or something. Temperature coefficient, so not brilliant, and I'll talk about that in a second. Because that's really, really important. And I'm going to use this chip here, a Max 6198A, which is a 4.096 reference chip, and it's rated at 2 parts per million per degree C. That's the version A part. So, that's about as good as you're going to get for just a couple of dollars, which is what these things cost. They're not expensive. I've got a couple of them here. They're about a couple of dollars each. So, I'm not trying to make this ultra stable, but there are some things to know about, how this works. First of all, this is an oven, so this thing will run warm. It doesn't run hot. It's just lukewarm, really. But one of the wise things to do is when we mount this, when we get this on a board, is to try and keep all the components located in such a way that the heat coming from this will raise the rest of the board's temperature up above room temperature. And the reason for doing that is all of these components around here, I mentioned earlier on, this is probably not that stable from a temperature point of view. In other words, if I was to measure its resistance and then, say squeeze it with my finger, so I warmed it up from ambient to my body temperature, you'd find there's drift. And that drift doesn't actually matter. What matters is that at any given temperature, it's predictable resistance, and as a general rule, resistors are. They don't have a a kind of shadowing effect, where it's, you know, once they're at a given temperature, as long as that temperature is a stable temperature, then you'll get, you know, pretty much precisely the same resistance. I'm sure there's more science to it than that, but that's my rudimentary understanding. So the thinking is, if I can get the oven-controlled oscillator, the reference chip, and the frequency and the frequency trim pot all sort of within close vicinity, mounted with some kind of thermal coupling, or some at least, you know, obviously keeping them close enough and taking away any other potential thermal influences, then that should serve to get a pretty stable stable reference. Frequency reference for this counter, which will be good enough. The other thing to do then is the physical construction. So that's how the circuit works. Really nothing complicated. These are all off-the-shelf components. As I say, that's about $2. I think that was, I think it was about $15 I paid for it. So they're the two components. As I say, a little bit of strip board, and we'll come on to the physical construction next. Okay, so physical construction then, it should be straightforward. Basically, I've got, look at this, is the original board. I've got a little bit more space in here, so I can probably get a little bit more width, except for at the bottom. So it'll probably have to be cut out something like an inverted T shape, and I'll do that and make that fit. So I'm just going to use this perf board. Obviously, I'm mounting all the components directly on the board, so that's straightforward. And there's none of these. Each one of these holes has, for those of you that haven't used that before, has you know, you can solder, and it's got a through hole plate, but there's no track, so it's up to you to join them. And as you can see on the back of this board, the way I tend to wire these up is I use wire wrapping wire, which is very easy to strip. It's very thin, very pliable, single strand wire, and just interconnect it that way. Hopefully let's see if that will focus. Yeah, just interconnect it that way. Hopefully I'll do a slightly tidier job than that quick hack there. Yeah, that's it. So I just need to construct it like that and build the circuit around it. So what I'm going to do now, the first thing I'm going to do is I'm going to go away and just cut a board to size and make sure I get a physical fit. Obviously with the connector mounted in the right place, and you know, the mounting point here, put in the right place. So basically I need to create a PCB with no components on it, out of this perf board, that physically fits into the counter and screws in and secures. So let me go away and do the cutting of this first as a starting point, and I'll come back. Okay, so that's the board I've cut. Now you can see it's actually slightly bigger, and I've tried to make it as big as I can get it reasonably, just to give myself more room, because obviously the OCXO is bigger. And actually it's like that. There's the layout there. You can see the connector will fit here, and the mounting hole is also drilled through there. Get that lined up, and that board should sit in there pretty much just about perfectly. So that's the board. Next thing to do now is work out how to lay this out. So before I do that, what I'm going to do is fit the connector on the bottom here and just make sure that physically fits in. So let me go and solder that, and I'll come back. Okay, so I've mounted that connector on there. I also I had to glue that down, and I mistakenly soldered that one hole closer to the board than I could have got away with. It could have come back one step, so as a result I've just had to elongate that mounting hole, which is a tiny little bit messy, but it wasn't an exact alignment anyway. So that now get that in there. That will now physically, you can see it fits in there nicely. That will mount and screw in. You can see there. So the next thing to do then is to look at the physical layout of this and see how we can fit all the components on. Okay, so unlike laying out a PCB, you have a lot of flexibility with these kind of boards, because obviously we're simply going to cross wire this, so we want to keep it as tidy as possible. But equally, we don't really have to give too much consideration to voltage, component layout, apart from physical layout. Now, one of the things that's really important is a physical constraint, so it's what you have to consider first. If you recall seeing this before, you'll notice that there's a hole here for trimming the, tuning the frequency standard. So it's actually quite critical, or ideally it's quite critical that we get that in the right place. So with the board mounting in here, this has to, I think it's somewhere around about, just about a few steps below here, so probably somewhere around about here, and obviously mounted on the back of the board, because that's going to sit in like that. We want the, it's not very clear on camera, sorry, that's going to sit into the counter like that, so this trim pot is accessible from the back of the counter, but probably the OCXO should sit on this side here. So let me just align that up and go and find the exact right position and solder that in place. Okay, so you can see here, I've temporarily mounted that, and if you have a look in here, that's where it lands up, right in there, which is absolutely perfect. So now we've got to now make sure that the rest of the components will fit around that, because that physical position is not really negotiable in this particular build. All right, so that's the trim pot mounted there, and obviously all the components now are going to be mounted on the back side of this. So looking at that, the first thing I would do, and this is my approach, not the only approach, but certainly an approach, is I'd now look at that, and there's only one obvious space for this OCXO to go in, because they're just physical limitations. So somewhere around about here, we'll probably do just about perfect. Now that means that the space we've got left has to be used for this other circuitry here, which is this voltage reference. Now the voltage reference is an SO8 package. So I'm going to use one of these small surface mount adapters, which you can actually get from Tindy.com. It's one of the guys on who also follows my blog, a guy called Mats Engstorm, sells these for $4.50 for a whole bunch of them. They're really good value. So there you go. If you need some of these adapters, then go there and have a look. So I've got to get that chip on here. So that'll be a simple case of using some some old resistor leg cut-offs and just solder that through, get that chip mounted. That'll sit nicely there. So that's that chip mounted, that's that mounted, that's that mounted. We've got a couple of caps and a couple of inductors, so that's about it. So what I'm going to do now is, I think that's all going to fit absolutely perfectly. I've put the other advantage of the reference being here is, of course, heat coming from this will rise, it'll go upwards, and it'll transmit upwards up the material as well, that's going to help bring this area of the board up here up to a higher temperature than ambient. Now you'll notice that I've cut away these metal pads around the mounting hole there, and when I put this together I'll use a nylon washer here. And the reason for that is I ideally want to isolate the thermal characteristics of the back panel, which is connected via, I'm not sure if you can quite see it from here, but there's a metal standoff coming from the back panel, which is a big chunk of aluminium. So obviously any heat generated around here, if there's good thermal contact between this and that metal standoff, then there'll be thermal contact to the back, and that will help pull this temperature down. We don't really want that. We want this to raise up to as high as this will allow us to get it. So I want good physical mounting here, but very poor thermal mounting here. And having both the trim pot and the reference IC above this helps with the temperature the temperature properties of this board. Okay, I'm going to go away now and solder this up. There's no point in me videoing that, I don't think. It's probably not going to be very exciting. So let me go and do that, and then I'll come back. Okay, so one of the things that you'll run into these sorts of things when you're constructing these things in this way is, this is not a standard 0.1 inch pitch. So what I've had to do, now it's fortunate that the actual centre pin is the one that's off, and I don't need to connect anything to that. So what I've had to do is put a hole in the board, because it sits right in between two holes, and I've got that positioned, if I can get it in, so that lines up there nicely, and obviously that pin is just floating around in that hole there, which is absolutely fine. So I need to hold it on with those 4 pins. Okay, so I've wired up the board. You can see there, that's how I've placed the components. Pretty straightforward. What I've tried to do with the surface mount caps and components is just mount them as close to the actual components that's appropriate. You'll see there on the back I've done the same. I've used bigger components where it's worked, you know, where it's made it easier to do that. And you can see down here inductor and a cap as well. I haven't worried too much about the tidiness of the wires. They are all flat and out of the way, so that's it. So next thing, I'm going to reposition the camera now, and I'll get this hooked up so we can give it a test. And I'll test this before I put it into the counter, just to make sure that it's not going to damage the counter. Okay, so what I've done here is I've just made up, just soldered a couple of wires to a small header. So I can get onto the various pins on this board. I've got a common ground from the power supply for the scope lead, and also the negative of a meter, so I can probe around. So what I want to be checking here on powering this up is, first of all, get something on the output. That's the first thing, and I'll set the current limit to what I know that it will draw. I have before I've powered this up, I have been round with the meter and just made sure, double check my wiring here. So it's a very simple circuit. You shouldn't really get this wrong. Anyway, so I'm going to power it up, make sure I get something comes out. Let's just turn on the scope so I can warm that up. I'm going to make sure that something is coming out, and then we're just going to check a couple of key points, because all we really need to check, assuming something's coming out, then we know the oscillator's running, so we know that that's okay. We obviously need to check that the pin 2 has got 5 volts on it on this voltage reference, and pin 6 has got 4.096 volts on it. And then we just need to check that I've set this pot to somewhere around about the midpoint, just an approximation. So just to make sure that the variable frequency control pin has got about half, you know, about 2.5 volts, something like that on it. So let's just set up the scope. Okay, so I'm just going to power it up, and there's definitely an output on the scope, so I'll just check these various voltages to make sure that we've got what we expect. So on pin 2 here we should have 5 volts, 4.98 and 4.99. On pin 4 we should have ground, and on pin 6 we should have 4096. 4076. Okay, I presume that's within tolerance of that chip. But as I say, the absolute temperature, the absolute voltage doesn't matter. It's temperature that actually matters. So that looks pretty good. Now, what I'll do, I'll leave that powered up now for about 10 or 15 minutes. Then I'll come back and we'll have a look at the scope and trim it out and see how stable it looks. Okay, so that's the oscillator running. I'm just going to trim that now and see. See, we can get this stable. Let's just bring this back here. So that's so from that to that is about half a turn on the 10-turn pot. So it's got quite a fine-grained adjustment over there. I'm going to leave that like that, and maybe give it 10 minutes and just see how that drifts. We'll see if that. All right, so I'll leave that for 10 minutes and see if it's still after that. Okay, so after 10 minutes, it's still rock solid, which is great. So I think what we'll do now is put the OCXO board back into the counter and see, and just make sure everything works. Okay, so here's the board now screwed into the counter. I've used, I'm not sure if you can see that, let me just bring the camera in. I've used a kind of plastic, just what you'd use for the TO3 or TO220 mounting. insulation. They're basically plastic washers, and that just gives me thermal decoupling from this board and this metal standoff here, which of course will be connected back to the rear panel. So that's it in there. So what we need to do now is see if it actually, when we power it up, see if it actually works. So let's just, if you remember from the last video, if you watched the last video, you'll know that this oscillator needs to be running for the actual microcontroller to work in here. So if, or the CPU, sorry. So by putting power on this, if it boots up, I mean, there you go. So it means the oscillator's running. So that's pretty good. All right. So the next thing, I guess, is to let me connect this up with the Rubidium frequency standard, so we can monitor the we can put the 10 megahertz reference in and just see how close we are. I'll also hook up the scope to the reference output, and I'll put the top back on this actually and get this ready, and then power it up and let it warm up. And once it's warmed up, I'll come back and we'll calibrate it. Okay, so what I've set up here, I've got the counter here with the OCXO board in it. I've also got the counter that I put the OCXO in last time, the HP, and I'm driving both of them off of the Rubidium frequency standard, which is just up here on my top right here. And these have been on now a good hour. I've let them warm up, and I've given that a little bit of a trim. You can see, when we had the board out and had it connected to the scope, I gave it a bit of a trim, and actually it's not that bad. But if you take it up to a 1 second gate time, well, it's about 2/10 of a cycle out, and we can probably trim that out, and I'm just going to try and do that now. Now at this juncture, the 2/10 of one cycle out is actually, there is a tiny little bit of movement in the scope and on the scope, and the reason why this is different now to when we trimmed it last time is obviously the thermal characteristics of that counter will be different as it's kind of warmed up now. So if you look at the signal on the scope, the top signal is the Rubidium frequency standard output. The bottom signal is the reference output from the Racal-Dana counter, i.e. the OCXO we've just put into that counter. And you can see it's very gently drifting off to the left there. So I can trim that back in, but also, at this level, it's worth, if you're going to calibrate this like this, the two, as well as looking at the scope, which makes it easier, having increased the resolution here on the gate time resolution on the counter. If I can get the screwdriver in here, I can't quite see the back here, but I think I'm on that. So if I give it a little trim, I should, if I'm patient, just wait a second each time. There we go, I can pull that in pretty much bang on. So yeah, that's I'd say that's pretty good. I'm pretty pleased with that. Yeah, I don't need to do anything else. That's great. That's really good. It's as stable as I sort of thought it would be. This 100 cycles that it counts every now and then, you'll also know it does that on this meter, and I'm pretty sure what that is I think the Rubidium, the way the DDS chip works in the Rubidium frequency standard, I think it adds or removes a cycle periodically to keep itself, where it's obviously got, it's not a precisely dividable frequency, I'm guessing, and so every now and then it compensates. That's what I'm guessing, because both counters do it, so I can't imagine it's the counters or the quality of the signal, because if you see, it's very consistently one cycle to 1/100th of one cycle. Quite interesting. But anyway, the average reading there is pretty bang on. Okay, so there we have it. I'll just have a look at this schematic. I've made a slight modification to what I showed you in the video before, simply because, of course, during the process of wiring up, I realised that I wasn't going to put all the current through the inductor. I had that here before. I've now moved that to here. The purpose of this inductor and that capacitor right there is effectively a low pass filter, just to remove any high frequency noise that might emanate from here or even from the OCXO. Around the voltage reference here, and it's just I almost certainly didn't need that, but I put it in anyway. It's not big deal for a couple of components, and so that's the schematic there as it now is, and as it's built, and as it's in the counter. So that's it. I think, you know, given how much that cost, it cost about $25 US dollars, or if you're in the UK, about 15 or 16 pounds to build that, to build that little board and do that upgrade on that counter. And what I would say is, if anyone's got one of these counters and don't have, and has that standard oscillator, this thing in it, if you're able with a soldering iron, I would definitely recommend you doing this modification, because it's really low cost, and that's a really nice counter, and actually that's improved it tenfold just by doing that mod. And for the cost of the $25, it's an absolutely blinding mod to do to the counter. Makes it really good. All right, that's it. If you enjoyed the video, please give it a thumbs up. All of the details, the schematic, and the data sheets and so on for the parts that I've used, you can find on the blog page that is associated with this video. You can get that just by clicking on the link just below the video here if you're watching in YouTube. All right, thanks for watching, and I'll catch you next time.